So last time we did a bunch of optimizations all over the place. And there's been some discussion of, well, optimizations in general and how people take it to ridiculous extents, which um I still do not believe. So Yotanido, I believe, pointed out that someone managed to complete the maze with a gate score of 2, which to me sounds beyond impossible. It's not even it's not even impossible because it's gonna be hard somehow, or it's difficult to implement some sort of algorithm just using 2 gates. But the simple fact that I need an 8-bit output and I need an 8-bit input and stuff. How on earth am I gonna operate 8 bits in one tick, or well, in however many ticks, using just 2 gates? Is it like an AND and a delay, and then you have some kind of crazy loop of the NAND going into itself? No, I have no idea how this is supposed to be possible. But I'm not gonna look it up until I complete the game. I don't want any spoilers for anything. So yeah, I'll just keep with my solutions for problems. And yeah, also I have been told that the optimal tick score for the maze is something like 700 something, while my tick score is 5k. So that's also interesting, although I assume they just use a more advanced, well, definitely they use a more advanced algorithm than my depth first search. But I don't feel like I have enough space to apply any better algorithm, so I'm also assuming they use a more advanced architecture for that, but again, I'm not sure. Now, something I wanted to point out overall with respect to optimizations is I did mention that I wasn't going to go to ridiculous extents, and that still stands. I do not intend to be optimizing things down to 2 gates. No idea how is that possible. How on earth? But to me, mostly I find optimizations interesting when they simplify the logic behind the thing. So one prime example would be the conditions level. And this kind of optimization, as opposed to my original, this is a very interesting change, and it really simplifies the schematic. It doesn't just save on gates, but it's an interesting change to the idea of it. And overall, I feel like the most efficient optimizations would be very unpretty and will complicate the logic of your circuit as opposed to simplifying it. So one example of that would probably be the counter, and I did go to where's my counter? Can I find it? Yeah, this thing. Right, so originally, oops, oh no, I lost it. Counter. The original solution is very simple. You have an adder that adds 1 and it's saved to a register. And this is a very simple idea. While the efficient solution to this is a huge mess. And this huge mess is basically an unfolded adder. So overall, I feel like a lot of the optimizations are just gonna be unfolding different gates into their guts, into their innards, and reusing the stuff from inside. So for example, in XNOR, if we take a look, this basically applies to any gate that contains, well, that's more than basic, more than just an AND. But whenever we have two things inside the gate, when I need, for example, if I need an XNOR and I need an XOR, in order to optimize my score, I would not use an XNOR and an XOR. I would unfold my XNOR, and I would have two outputs from it, right? I would take this as one output, and I would take this as another output. And then I would always reuse the XOR, or I would always reuse this node. And this applies to everything. Like if we take a look somewhere else, well, yeah, an XOR also works, right? I could, instead of having a single XOR input, I could have a fused element that would be an XOR or NAND element, right? And whenever I needed these three, I would use this kind of thing. But I think while they would optimize the score, they make the circuit more complicated, and I want to avoid that. I am mostly interested in simplifying the logic behind the circuit. Now, yes, I do sometimes go to some extents to optimize my score while sacrificing some simplicity of the circuit, but still, I don't want to go too deep into that. So, while we're at it, I still have a bunch of work to do with my stack. This is completely unchanged, but last time this is what we ended up with. And there's still at least one optimization going into the guts of things, which is these two muxes. They are decoded by basically the same thing, right? These two inputs are complements of each other. And since they are used to decode my muxes, I can decode them once and then pipe them into switches manually, or well, do something else. So that would probably be an improvement of my score. There's still the question of, well, just rewiring this to be a compact little element. And there's also the question of what happens when we have both a push and a pop happening at the same time. I'm still not entirely sure what I should do, but I'm inclined to probably just passively, aggressively telling that to never happen, you know, something along these lines. So I'm sacrificing a little bit of a gate score of 1 to put this end, but I also build a wrong operation protection into my circuit this way. Oh, and also one more thing I was going to go into was specialized constant adders. If you recall, this originated with the counter level again, where we built a purpose-made counter with with +1 increments, but we got a +n counter for free. And I'm wondering how much a +n custom-built component would cost. So, where should I start? I think I should probably start with these muxes and cleaning this up. And I might go into the custom adders later. So, this is probably best done off camera. I'm gonna rewire this and I'll be back. Something along these lines. I'm not sure I haven't broken it in the process, to be honest. But yeah, the idea is the same. We have a loop that is pretty much always increasing or decreasing, right? We have plus, plus, minus, minus, loop to register, except every time we select whether we save the plus, plus or the minus, minus, and that's decided by a decoded output of this guy. So yeah, I basically ditch the push input completely and it's only used to recognize that, well, I need to do something. Otherwise, everything is decided by this decoder, which is decoded from the pop input. So this decoder decides whether we're pushing or popping, and so right now we are pushing, and green line for save means push. So we're currently pushing, which means we are incrementing our address. So this switch goes, and we save the address, and then the output of this loop, which is the actual address, is either what's saved or what has just been calculated. And I mean, interestingly enough, this also feels a little bit redundant because yeah, I think I could even get rid of another switch, because these two switches do the exact same thing, right? They if this is on, so right now this is in fact on. This switch takes ++ as the input, it passes it forward, and it also goes into this one, and this one is also on. So when we are ++, we need to make our output not what's saved, but what was ++. So I think I can literally just remove that entirely, like so. It's a shame I cannot test it, but that's good. This switch still needs to stay because it's a different input and output. Yeah, but I can now simplify this a bit. Something along these lines, maybe even pull it down a little, like so. Right, and then we have this kind of structure. Does this look good? Oops. No, I think it's wrong. I think it's, wait, yeah, I think it's wrong. Yes, this is wrong because, of course, in this case, when we are green, I don't need the switch, but I also need the switch to be off and to prevent my -- from conflicting with the output of this. Yeah, so I do need both switches. Okay, well, all right. So yeah, and they are piped into the address pin of our RAM. We also only save to RAM when we are pushing, so green to save. We always load because we have a switched output, so that's fine. This on should be good. And yeah, the saved value is just the saved value, although I did pipe it into a weird pin, right? Normally it would be this one. I don't know. I feel like risking it and piping it into here. I think these pins should be equivalent. Should be no different. Also, why? Oh. Wait. Did I mess this up? I think I messed it up again. What did I decide on? I think we are, if we are pushing, yeah, I think I wired these backwards. If we are pushing, then we're pushing to the current cell and then incrementing, and if we're popping, then we decrement first and then we pop. Yeah. Okay, I need to rewire these. Give me a second. Right. So yeah, I just switched the wires around as well as these operators. So these lines, this is just for symmetry. So yeah, now if we are popping, or well, let's start with pushing. Right now we're pushing and we are incrementing what's saved. That's the case. But the address we are actually reading from, or actually writing to, is going to be what's currently saved and not the next thing we save. And vice versa, if we were, well, I guess I can quickly pipe an on into here. Let's take a look real quick. If we are popping, then we decrement, that's fine. And yeah, the address we're actually reading from is the previous one and not what we're actually pointing to, so that's good. I think this should be fine. Now, there's a problem with this. I am using a lot of custom components in here, and they are actually pretty huge inside. And if I were to try to implement this in the actual level itself, that would be quite difficult. And I'm not sure I want to do that. So I think I'll leave this be for now, because I can't be bothered. And I'll proceed. I'll test if my actual factory component works. And then, if it does, then I can go and implement it. Maybe I'd probably do this off camera. Okay, so let's proceed. I think. Okay, what is this? What is this? This is Overture. This is Overture. This is Overture. No. Oh no. This is Overture. Everything's going wrong. Why is this Overture? I want leg. I didn't optimize my Overture. I don't know how Overture works. In this level, you're supposed to add the stack to your computer and write the program that solves the level. When the input is 0, you should pop a value of the stack and output it. When the input is not 0, you should push it on the stack. Why in Overture though? Why in Overture? I have leg. I have fat leg. Leg is so pretty. Whatever this is. What is happening? My leg has no RAM register. What? This leg has RAM register, but that doesn't. I'm really confused with what's happening here. As well as with the fact that I am now supposed to work on Overture. I would probably want to optimize Overture first. I don't think I'm gonna be optimizing Overture today. It's a shame. It's a shame that I have a cool, clean, streamlined, optimized new leg, and I'm forced to use Overture. Although, could I do something crazy like switch schematic to leg? Wait. Switch schematic to leg 16. Oh, wait a moment. Can I still... Oh! Wait. How is this the case then? I can just switch schematics for a level. Okay. All right. No, I'm happy with this. I'm happy with this. Okay. So let's solve this with leg then. So let's take our stack, and what do we need to do? Well, we need to incorporate the stack, and this is gonna be another design challenge in the same way as I found adding RAM to be a bit of a challenge. Hopefully I can solve this one easier. So we definitely don't have an address on the stack, right? The stack has a pretty simple interface of pop and push, so we don't need this white line or anything like it. But we do need to pipe in a value to be saved, and we do have an output. Well, this actually still kind of looks like a stack register. So here's what I'm thinking. This is my initial thought. My value is what I'm saving, right? This is my save method of my interface. And if I'm pushing, then this means let's just use stack as the whatever the number will be, 9th or something, as the 9th address, as the 9th register. So if we're pushing, right, then we're going to be pushing the value from our output line. But now there's a question of popping and this output. That's a bit more interesting. Although I think I can do this the same way I do the input, right? This is the exact same setup. So I can use an OR with both inputs piped into the OR. Right, so let's take this and let's take this, right? Something along these lines. And then we'll have these switches in the exact same way, like so. Oh, wait. Okay, let me wire this up. Right, so here's my stack register. Yeah, the idea is exactly the same as for everything else, and it's especially reminiscent of the input. So we can control whether we pop from stack to input 1 or to input 2. We can also pop the same. We do pop the same value for both. So if we pop, we can just get 2 copies of the same popped value. We don't pop twice. And if we pushing to stack is equivalent to saving into the stack register. I think this should work, and I think I'm actually ready to proceed with assembly. Oh, I'm so rusty. I don't remember any of my assembly. Yeah, this is gonna take me a little bit, but well, first I think let's add. So let's take a look here. We have our RAM register, and that's an 8. So my stack. Let's add a stack address. Is gonna be a 9, and this is gonna be stack saved. Okay. So, do I need anything else? I don't think I need anything else at all, right? And I'm just ready to implement the solution, except I don't know where to begin. I'm so rusty with this. So when the input is 0, I should pop a value of the stack and output it. Okay, well, it seems fairly simple. Except I don't have a mov. I remember that. I have in order to do a mov, I need to perform an add to 0, I believe. But how do I do? Oh goodness, how do I do an immediate 0? Yeah, okay, immediate 1, I think, and immediate 2, right? So it's something like add immediate 1. Is it 0? And then no, actually add immediate 2. I want, oh my goodness. Yeah, I want 0 to come first. So let's say stack IO. So is this gonna be my assembly instruction to pop from stack and output to IO? Is this right? See, I forgot everything about my architecture. How can I? Oh, you know what? Yeah, I don't feel like digging into the architecture itself, but I do have. No, this was in Overture. I do have some assembly solutions, I believe, at least one simple one, somewhere. Where's my... No. Wait. What? I'm pretty sure I did at least one solution on my Overture machine. No, what? Oh, sorry, not Overture, on my leg. Right. It was RAM. It was RAM. And when I added RAM, it was not just about adding the component, it was also about me implementing a particular program that would utilize RAM. So let's take a look here just to remind ourselves. Yeah, so this is what I was using. This is right. So immediate 1 I add. So I add 0 in order to just mov. And I mov from IO to RAM. And this is, yeah, add 1. I don't know what. I don't know why I needed a plus plus. What did it want from me? Oh yeah, I was doing plus plus in order to emulate a stack using my RAM. So yeah, okay. I am remembering my architecture correctly, except let's do... Wait, why did I do immediate 2 then? Immediate 1 was right. So immediate 1, 0, stack IO. So this will pop from stack and output to IO. Okay. But what I need to do is, if the input is 0, I pop. But yeah, so first I need to take my input and compare it to 0. Okay, do I have a direct 0 comparison operation? Yes, I should have it, no problem. So, an EQ, do I have an EQ? EQ, okay. So, oh goodness, I have no idea what EQ does. EQ will do a conditional jump. Right? Oh no. Give me a second. I need to remind myself how I did these things. Alright, so in leg, the condition is separate from the jump. Well, at least the way I defined it. So it's gonna be jump EQ. But I want jump if equal to 0, right? So I will also want immediate 1. So if we're equal to 0, and that is if my IO is equal to 0, then I pop, right? And I disregard the value of IO. Oh, but I don't, right? But if it's not equal to 0, then I have just lost it, right? Because I read it and it's no longer there. So actually, I think it's not enough for me to do a comparison directly on IO. I think I will need to load IO into a register first. So let's just load into A. Okay. So let's do... You know what? Do I wanna... I'm thinking of defining... I'm just considering either I wanna do const I1 add is mov, or I wanna add mov here. This feels more modular, right? I don't want to hard code the thing that actually unfolds to a definition. Only name and value goes after const. Oh, so name first, then value, sure. Const mov, one add. Okay, I think I'll go with const for now. Although it's still weird because I'll have to do... I cannot define multi byte constants. Can I do like const dot 0? So now I can do mov dot something. Does this even work? Is this dot defined? No, I don't think this works. Although it's not complaining about an error. Can I do const underscore 0? Yeah, so underscore is clearly recognized. It's different color. I don't know. I'll go with underscore until a better idea comes to my head. So I want to load from IO to, let's say, A, doesn't matter. And now I need to check if my A is 0. So immediate 1 jump if equal to 0A. And I need a label to jump. What I need to do is I need to pop, right? So I need to pop. So let's do a label pop, label push. I think I'll also need a label loop. So if we're 0, then we pop, which means we move from stack to IO, right? And if we push, then we move from IO. No, it's not from IO, it's from register to IO. Oh, sorry, to stack. I think that's about it. Well, except I still need to loop back. So, oh goodness. What's an unconditional jump for me? It's gonna be something like immediate 1, immediate 2, jump equal 0, 0. I do remember Christopher pointing out that it would make perfect sense. I think it's Christopher, sorry if I'm misremembering. Pointing out that I could do something like this, and this is actually equivalent. But since it doesn't take more bytes, I would prefer, just for my sanity, or for, you know, in order to feel better, because this feels better, this feels like constants as opposed to loading the values of the same register, and I always am a bit worried about loading things from the same register and assuming them to be the same. At least when it comes to a real programming language. This here, of course, is not a problem, but still, I want to make sure that nothing changes, that the register's value does not change between the loads, and I want 2 zeros. So let's jump if 0, 0, and we jump to loop, right? So this is that, and the same needs to happen at this point, and I think this is my program. Right? Is this right? I think I could... Oh, yeah, I don't actually jump to push. I don't have such a label. And what I actually need to do is just do it here. Right, so this is an if construct. Okay, let's try it. Let's check. I expect this to break horribly. Also, I don't have any way to look inside my stack. I think it would be helpful to add a thing. Okay, let's step move from IO to A. That worked. So we loaded 18. We're not popping, so I expect to go to the stack. Yeah, that's 18 being loaded to the stack. Perfect. Being pushed to the stack. And then we loop. And then again we read from IO. Okay, so this looks good. Except, yep, you were supposed to pop the last value. I'm afraid my stack might be broken. It actually looks like it is, isn't it? So we are loading from the stack, we are popping, but the value seems to be 0. Okay. Time to fix this piece of junk. Oh! Oh, it looks like we have... Wait, what? Why is this on? Why is push on? I'm currently popping. I don't understand. What? Okay. Okay, I'll debug this and I'll be back once I understand what's happening. I must say, after looking at this for a couple minutes, I don't actually see a real problem with this. So I would like to see this in motion. I'd like to see this actually used. So let's try to add the probe. Let's try to inspect the contents of the component while we are actually running. So, is a memory probe good? Would a memory probe do? Something along these lines? Yeah. Let's try. Let's try and see. So this is gonna be showing me. Well, I expect it to be constantly showing me zeros, basically. Well, except well, so long as I'm pushing, the stack pointer is gonna be constantly on the next location, and the next location is constantly gonna be zeros. Yeah, so unfortunately this doesn't really help. Push, push, push. So I keep pushing. Okay, but pop. Pop. I popped a 0. I don't really understand. Maybe this is coming to bite me. Let's try rewiring it in a way that I understand. Oh, I think it just popped. Yeah, I think it's popping correctly. Okay. So it was as simple as that. Cool. Except this memory probe, we can now clearly see is completely useless. I wonder... Oh, maybe I could... You know what? Maybe I could at least connect it to the stack pointer. At least that would be helpful. Yeah. I think that's an okay diagnostic thing to have. Yeah, let's put it up top. Like so. Did I connect it? Yeah. At least we're gonna have some idea of what's currently... Maybe I could also use a wire probe on the output. Like so. This would be my actual output. I'm not sure how useful this really is. And especially I expect to get confused which of these two is which. Which is the pointer versus which is the value. So let's remove the pointer and let's try to do that. I understand I can always see the wire. Yeah, and besides, no, what's loaded is not... What's loaded again is mostly gonna be these pointless zeros because that's the next value. So now let's go back to the pointer setup. Go back to the pointer setup. I think that's gonna be slightly more helpful. At least I can see that my stack is large or small or something. Okay, so let's complete this. Done. Push and pop. Stack is introduced, and I love the fact that it's still a stack gister. The fatness of leg is paying off. Cool. Let's proceed to the next level. By the way, I've never mentioned this, but I feel like mentioning it now. I have not forgotten about my promise to do plus plus, minus minus, and you know, adding constants. But I just feel like it doesn't fit in right now. So maybe I'll do it at the end of the video. Maybe I'll do it in a separate one. But for now, let's proceed with functions. Okay, looks like we're gonna have the function call stack. Sometimes it is useful to reuse a section of code. We call these sections functions. To implement this reuse, one can jump. What is jump? Okay, terminology. Oh, jump. Wow, I've never seen links to the manual before. I think this is the first use of such a link. But okay. one can jump to the beginning of the function and jump back again at the end of the function. Yeah, I even implemented the assembly for that, except I didn't have the stack back then. And, well, now I have a stack. So we call jumping to the function calling the function and jumping back from the function returning from the function, sure. But for this section of code to actually be reusable, the return jump will have to be able to return to different locations depending on where we call the function from, yes. You could save the counter value to a register before jumping to the function and use this value when returning. However, if done this way, a function would not be able to call another function, since this would, well, theoretically, hypothetically, you could save to another register and then you would be fine, but then it's just that your call stack would be limited. Call stack, air quotes, would be limited in depth. However, if done this way, a function would not be able to call another function since this would overwrite the original return address. Say function A calls function B, who calls function C. This is obvious. Okay, when we want to return from function C, we only need to return address for B, and in B we only need the address for A. In general, regardless of which function we look at and how they are nested, the last return address we added is always the first one we will need again. This is exactly the behavior of the stack, yes. In this level, you are tasked with implementing function calls and returns with the call and read instructions. Ooh, okay. Wait. I can't do it in a single instruction, I don't think. Well, okay. Note that when returning from a function, you should jump to the address that came after the call instruction, otherwise you will end with an infinite loop. Okay, that's good call. The call instruction has to do the following. Add the instruction width to the counter value and push it on the stack. Aha. Jump to the function address. Wow. Pop return address from the stack and jump to it. Okay, that's actually... This is interesting. I've never considered how exactly this is going to be implemented. It seems pretty obvious in abstract, but yeah, the adding of instruction width and everything is an interesting challenge. So you can pass information to and from a function by saving the data to registers as normal. Also be aware of which registers a function will override before calling it. Well, I would say that I did already mention this a while ago when I was first playing around with functions. I would mostly call these not functions but subroutines for now, for assembly, because basically we don't really pass anything and don't really return anything, but rather all these functions operate in exactly the same environment, right? Well, up to the stack, I guess. So really, I don't think it's particularly helpful to think about return values and arguments to functions. Okay. Wow. Alien guy. Budget cuts have led to cutting salaries, but now the lab assistants are on strike. You will have to self-assess in this test. This test will tell us something about your honesty and maturity. How is that elephant doing, by the way? I assume the elephant is eaten. Level is complete. I honestly, I think the developer just didn't have the way to implement the test for this level. But okay. So all we want is a call instruction. What does my call need to do? Let's try to write it using our current instructions. So we want to push the instruction on the stack. I'm still worried about the fact that this is supposed to be a single instruction. But we need to do two things. We need to push the stack and we need to jump. So it's really going to be two things. Okay, well, so what I want to do is I want to add, and I just want to add, what I want to add is my IAR. Was it? Yeah, IAR, instruction address register, which is the counter. So this is, wait. Where? Yeah, so my counter points to what instruction I am at. And I want to add one to it, one instruction, but an instruction is 4 bits. So I think this would be an okay thing to add as a part of my ISA. What do I call this? This is too long. I'm tempted to call it IW for instruction width. Just so I'm even more confused next time I forget how my assembly worked. And my instruction width is 4 bytes. So, oops, 4. You know what? I'm gonna look up a an accepted notation for instruction width. Nah, couldn't find anything. But I think instead of IW, let's just call it width. Except I cannot accept something that simple. I'll call it width. Yeah, in case you couldn't tell, I like these esoteric names. So we're adding instruction width to the instruction address register, and we are putting that on the stack. Now, once we have done this, we want to jump to the function address. So we do an unconditional jump. Should I do something like const unconditional jump? I don't know. Unconditional jump 0 0. No, underscore underscore. Unconditional jump to, well, the function address. Label func. Let's call it func1. And let's say our func1 is gonna, well, let's just increment register A. So let's do immediate one, add 1 to register A and put it in register A. And now what we need is we need a pop. So, well, I just unconditional jump to stack. Is this right? I think this should be right. So, and now, this is my function call. This is my function. I can put this in an infinite loop. Label loop. Oh, test loop. And let's do unconditional jump to test. I'm really lacking, really missing, but really wanting multi-byte instructions or multi-byte constants. Okay, let's test if this works. I didn't name my last program, did I? Funcs.oml. Wait. Do I have a name for leg assembly? I don't. Well, it's gonna be LML, isn't it? Leg machine language. Funcs. Come on. Leg machine language. Cool. Let's go. Let's test this. Ooh, looks broken. Wait, actually it doesn't. It looks like it's working. Let's take a look. No, it's broken. Why is it broken? Why are you broken? So, we push the stack. I don't know what's on my stack, unfortunately. We jump to function. We add one to A. We put it into A. We pop from stack and we jump back. This puts me at the unconditional jump to test. What? How did it pass through the unconditional jump? Am I adding too much? Is my width too big? Oof, that's unfortunate. Okay, let's try to maybe take a look here. So we jump by 4. We jump over. And then I think it jumped wrong. How much did I add? I added 4. Do I need to add like 5 or something? Am I off by 1? Yeah, so I expect to jump to the 2 to 4 place, and I don't. Yeah, so my program is just completely borked. Let's try and replace width with 5. I don't understand why I would want 5. Or is it 3? Oh wait, no, it's not 3, it's 4. I don't understand. Guess let's try 3. Let's see what happens. No, it's still broken. Why? I don't understand. Yeah, see, this is 0. This is 4. Oh. Wait, I actually need to... Where I need to jump is I need to jump even later. I need to jump to 8. So do I add double width? I think I can use this in my LML. Let's try that, I guess. Let's see what happens. No, still broken and off by 1 for some reason. I'm confused. What? Yeah, whatever. Four. It's a real shame I don't have insight into my stack. What did I save to stack? Let's try and take a look just by inspecting the wires. So right now I should be saving AAR plus 2 times width to stack. But the output is 0. Why is it 0? Okay, let's remove 2 times because I'm not sure that works. So width is... No, that's not what I wanted. So at this point, I am saving to stack. I'm pushing to stack, right? This is green. But what I'm pushing to stack, it's the output of my ALU, right? My ALU is on, but it's outputting 0. Oh, but it's... Oh, I need... Of course, I need add immediate 1. I prefer immediates to be on the left. Okay, let's fix the width. Set it back to 4. I don't know how it even worked before. But now that should work, right? Now this should work. Let's try. Yeah, I'm pushing 4. Though this is probably wrong and I probably do want to push 8. What? No, we're running away again. What is happening here? Something's wrong. So I push 4 to my stack. That's cool. Now I jump to my function, and that works correctly. I have jumped to the function. Now I increment by 1. And now I expect to jump back to whatever is on the stack. But nothing's loaded from the stack. Yeah, my conditional block is on. And I am piping an instruction into it, but the inputs... What is happening? The inputs to the conditional block are not... Yeah, and I am saving to the clock. But the inputs to the conditional block are not there. I'm not loading from the stack. Wait. Wait, I think I'm confusing things again. Do my jumps jump to constants? I think my jumps jump to constants. Wait, how do I jump to... Oh. Right, jumps jump to constants. And this is currently interpreting stack, which is probably helpfully, yeah, a 9. And it puts me exactly here. Or, well, wherever. Yeah, and what I actually need to do is I'm not an unconditional jump to stack, but in fact, I am move from stack. Move. From stack to the instruction address register. Yeah, okay. Let's test this now. I think it's working. Is it? Yeah. +7, 8. Yep. We're ticking up. Great. My subroutines are working. Well, since I am supposed to test myself, let's also double check that I can implement nested functions. So let's say label function 2. And let's say function 2 is gonna add 2 to register B. Right, and this is all the same. This is still a pop. But from here, I'm gonna call... From here, I'm gonna call function 2. I am opposed to foo and bar, by the way. I really don't like foo and bar. I hate it when people use foo bar. I find it confusing every time. Okay, let's test this. Ooh, this doesn't actually look exactly like what I expected. Because would this not mean that register B should have double the value of register A? And instead, it seems to have a much larger... Yeah. It looks broken. This looks broken. We added twice to register B. Well, I should have only added once. Let's try to add 1, just so it's a bit clearer. Yeah, so 1. We jump to function 2. We add 1 to B. I did push the stack. But it put me back on the unconditional jump. What's wrong? My stack is 1 long. I would expect my... Ooh, 255 then, huh? Oh no. I am popping from... It looks like I'm popping from stack more than I am pushing to stack. That's weird. So... Weird. This is really weird. What is wrong? Okay, I think I need a moment here. Okay, so the fact that we pop twice is not really the problem. The fact that we pop twice from stack is just a side effect of the fact that we call F2 twice. And it looks like the jump back from F2, the ret from F2, puts us back at F2. Whoa. Cut, copy, paste, select all. Wow, there's a right click in this editor. I never even noticed. I just clicked accidentally. Okay, so yeah. We have pushed the return address for F2 to stack. But when we actually return, we get back to F2. And now from this, I expect we're gonna immediately pop out into the loop. Because this seemed to be correct. Hello? Random freeze for my PC again. Yeah, so from this MOV, see? From this one, we're never supposed to jump from this one back to the main loop. But it's weird that this works, and its exact copy over here doesn't. Right, so adding +4 here does put me back where I want to be. Oh, or does it? Oh, it doesn't. Okay, right, so I want 2 times width. Right, see, this is the kind of thing you don't notice until you do a more rigorous test. Because it doesn't matter to me if I'm looping in this function just because I'm jumping back to the function immediately, or whether I'm looping through this loop. So I think I want 2 times width. Let's see. Yep. Perfect. So now these registers should be perfectly in sync. 5, 6, 7, 8. Yep. Cool. Okay, great. This works. I think I'll skip the 2 times width. It's a major shame. I would like to call this entire thing a ret, and I would like to call this entire thing a call. Well, actually, even this bunch, but I don't think I can. There's no way to define multi-byte instructions. I'm gonna go and try to take a quick look at Discord. Maybe there is, and I'm just missing it. So if I find something, I'll tell you, and I'll be back. No, I can't seem to find anything. I even tried just defining literally, if we take a look, a large constant. So if I define something like this, you know, and then, well, const, whatever, n. And if we take a look, it's not actually a multi-byte constant. It just overflows, right? When it doesn't fit, it overflows, but it's still a single byte. So, I don't know, 0x, 0, 0, 0, 0, 0, no, 1, 1, 1, I don't know, f, 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 f. This doesn't even work for some reason. Doesn't even do anything. Oh, it does, okay. Yeah, it just doesn't work. See? So unfortunately, even though this level is asking me to implement an instruction, the call instruction, it looks like what I'm gonna have to do is I'm gonna have to copy my, you know, manual code. What? Manual code every time. So let's mark this level as complete, I guess. I think we've done well enough. Can we trust you? No. Feel better of you. Oh, the level is complete. Can you trust me? Yes. Ooh. Complete the functions level. Tutorial complete. Thanks, team. Onwards. All right, tutorial complete, and we are ready to proceed with what looks like a million assembly challenges. But only after I am actually done with these levels as well. So that's gonna be all the levels for today. But I think as bonus footage, I'm gonna go back to my problem, or to my idea about constant addition. So just to remind you for the millionth time, if we take a look at the counter level, when we implement the counter this way, this is an optimal way to implement a counter that counts by 1. I think it's fairly efficient. I think there's probably improvements for this. There's probably more efficient addition or something. But we have hard-coded a plus plus operation into here, but when we run this, wow. Come on in. Okay. We get a counter for which, if we take a look, for which we can set an increment. And this counter costs the same regardless of what increment is set, right? This is gate score 53 and delay score 20. And I was wondering whether we cheated the system by implementing the plus plus and getting this for free. I think the end result is no, we didn't. And in fact, this is the most expensive a counter can be. I think a counter that counts by 1 is the most expensive counter. And then there are counters that would actually be cheaper to implement. And I think I might even want to implement my +4 counter as a custom component that is cheaper than a ++ counter. So, but first let's try to take a look at the more generic question. Let's go back to the adder, adding bytes. Let's copy this. And let's go into the factory and let's play around with this for a moment. Let's add a new schematic called add const. This is not going to be used much, I imagine, but still. So, like I've already explained, this addition consists of just 8 single adders. And really, if we think about these in abstract, actually, if we think about any element in the abstract, what these are really is pure functions on bit inputs. So really an add, we have 3 inputs. These are bits. I'm gonna call them booleans for this particular example. So really what we have is we have a function add that takes a boolean, another boolean, and another boolean, and it returns a pair of booleans, right? This is what happens, and basically all the gates are this way. Now, when we have an input that we know, when one of these 8-bit inputs is constantly known, then the second argument of this add, this part, well, actually, this is going to be the carry. This is going to be first, and this is going to be second. This one is going to be known. So basically, we can kind of partially apply these adders. So we can say, goodness, I can't really swap them around, but just roughly, let's say, add something something to 1, right? And this is going to be a function of 2 arguments, and it's going to have the same outputs, right? This is rough notation. And by knowing what this 1 is, we can reduce our adder. We can take a look inside, open it up, and knowing that the 1 is there, we can reduce it. But actually, it doesn't really matter whether it's a 1 or a 0, right? It remains the same. Now, that's just one way, one thing we can improve. But a whole other thing that can be improved in some cases is actually this carry line. So, for example, let's just imagine for a moment that what we're adding is not a 1, but what we're adding is actually 128. Now we know that this is a 0, as well as this, as well as this, as well as everything, right? So, and well, for us, no, since we're adding constants, no carry in exists, so this we can just completely disregard. But basically, we know that nothing happens to this first bit, which means we can completely remove this addition. So really, for this first adder, we already know that the carry in is also 0, right? Which means we can remove a whole other argument. But now that this carry was 0 and this is 0, we also know that no carry will happen, right? Because we added nothing. Which means that the next adder will actually have the same form. Something like this, right? And this will actually hold true for all the adders up to the very last one. Except for this one, we can completely disregard the carry out, right? As well as in the same way that we could completely disregard the carry in just because we don't need it. So I believe, just through quick, I don't know, just by putting a couple of minutes thinking about this, I believe an adder that adds 128 is probably going to be the cheapest possible adder of them all. The cheapest possible adder that adding a constant. Well, barring one that's adding 0, of course, that's gonna be nothing. And if we go back from 128 and we add some more bits, right? The same reasoning about the carry line still applies to these first n adders until we get to the first non-zero bit of our constant input, right? So at this point, we are going to want to add the carry line. So this we don't need, and these can be reduced. But these ones we still need, and it actually doesn't really matter whether this is on anymore, right? Because imagine this is all ones. Once we add this one, we're gonna have a endless cascade of carries all the way down. So in the same way, just because we cannot remove the carry line from an add 1, right? Because the carry line starts back here because we're adding 1 already. I think the plus plus adder, the constant plus 1 adder, is actually going to be the most expensive one of them all. I think anything odd, anything that contains that one is also going to be at least as expensive as this one, or, well, somewhere in the vicinity. And the cheapest ones are going to be the ones that add large numbers like this without small components. So now that I've gone through all this, I am actually curious to implement all options, all variants of these partially applied adders. And out of them, I think I would be able to build an arbitrary constant addition gate. So let's try to systematize this a little bit. So what I need is first of all, for each partially added argument, I will need an adder that is capable of carrying and an adder with no carry. So we will have carries, I think carry, and we'll have a non-carry. No carry, I guess. Variants of the adders. So the no carries are going to be these ones, and then the carries are going to be these ones after something happens. And we need a carry adder. We need a carry add. Well, carry plus the thing. We need it to add 1, and we need the same thing to add 0, right? As well as non-carried versions of them. We need, well, actually we don't need this one, right? Because non-carried addition of 0 is nothing, so we don't need this. And we do want a non-carried addition of 1, but it will have a carry in its output. So I think just out of these 3 building blocks, I should be able to implement an arbitrary, an arbitrary constant byte adder. So I think I'll go ahead and I'll try to implement these. I'll just base them on the design of the full adder. So I'll just take this and I simplify it. I think I'll spare you my stupidity and I'll implement them off camera. So I'll need 3 things, these 3. Yeah, let's start a little bit and then I'll do the reduction myself. So we need a carried add 1. We need a carried add 0. We need a carried add 1. And we need a non-carried add 1. So this means that this can be removed, right? These need to be here. But this doesn't need to be here, which means probably something. Yeah, this is a bit confusing, but now the carried guy, for this one, we know that we're adding a 0, right? And for that one, we know that we're adding a 1. Oops, not an off, an on. Right? So it's this one, then this one, then this one is what I'm trying to implement here. And for the non-carrying one, since we know that there's no carry in, we have an off as our... Wait. Well, yeah. It's a little bit confusing that I don't have an off, right? The non-carrying add 0. You know, just for completeness, I think I might want to implement it, even though I think it should have a cost of 0. But I would still probably want to implement it. It's just a couple of inputs and outputs, so I can plop the same structure of a component into my schematic and just be able to reuse stuff. So yeah, I think I'll also implement one of those, even though it'll cost nothing. So yeah, next time you see me, hopefully I will have figured out how to reduce all these and have created the 4 separate components for them. By the way, another thing I just noticed, well, let me, so I want a add 1 here, I just forgot to put an on. Another thing I just noticed is, even though on my whiteboard I was writing the notation as if my constant addition, my known partially applied argument is the second one, So it would really be this, right? This is my second input, right? Remember, it was like this. But actually, since it doesn't really matter which is which for the output, I think specializing it earlier in the chain, right, using this off applied here, might improve my ability to reduce this thing, right? Because if I apply it here, then I'm only able to reduce this much, while if I apply it here, I should be able to reduce the entire thing. Well, at least theoretically. So I'll also play around with this. Maybe I'm wrong, and maybe this is actually more efficient. So I'll probably try it both ways. But yeah, the plan is still the same. Right, here we go. I have defined all four, and I even tested them. So we have +0 with a carry in, and well, the carry out. So these, let's first talk about the naming. We have +0, +1. We have carry and no non-carry, but carry and non-carry really means whether there is a carry in. The out will always be there as necessary. Now I decided to keep the same interface for them all. So for example, even though +0 no carry in is literally just take the input, put it to the output, and our carry and, well, carry in and carry out must be off, always. Even though this is not necessary, I just decide to keep them in the same shape, so I believe I should be able to just replace them, you know, in place, in situ. I don't know what the word would be, without changing the schematic. So they just fit like Legos. Same thing, +1 with a carry in. This is the most complicated one. I'm not sure if this could be improved. This is what I ended up by when reducing the full adder. This feels a bit convoluted, but I guess it's warranted, especially considering we are still adding up to 3 numbers here. And +1 non-carry, also absolutely simple, except, like I said, while we do not expect any carry, and I actually explicitly piped it into off to get short circuits, we can get a carry if we're adding +1 to a 1. So now, let's go back to our add const. Let's remove all these. So, well, I mean, I can just so it's clear, I can show that this is my +1 carry. This is my +0 carry. This is +0 non-carry. This is gonna be, well, +1 carry is what? +1 carry is this. And then +1 non-carry is this, right? And they're all the same shape. Now, based on this, let's implement... Well, let's start with what we already know. Let's implement a ++ operator. So a ++ operator is going to be +1 with no carry, right? We start with a +1 with no carry. But this can possibly start a carry, right? If we imagine we're adding to all ones. So this would be 1, we're adding 1, so we start a carry cascade, and we will need carries all the way down. Which means that all the way down, I will need to put down +0 carries, right? Because I know that I'm adding +1, and 1 is fixed, everything else is zeros, so I'm doing +0s. But since I am carrying, I will need the carry blocks. So, now that I'm looking at them, I think I could even improve the structure a little bit. Whatever. Let's just use this. So 1, 2, 3, 4, 5, 6, 7, 8, right? This is our setup. And now we pipe 1 into 1. I wonder why this pin is square like that. Does this mean it's grounded? Because it is. I'm not sure. No, well. So yeah, 2 we pipe in here, 4 we pipe in here. So absolutely basic stuff. Actually, I'm tempted to do, you know what, I'll do the grid layout. So something like this, just simply piping bytes into 1-bit gates. And what we need to do is we need to add our carry line. Wait, oh no, I messed up. Okay, give me a moment. Yeah, my outputs are all up, so I think I can just shift this by 1. Like so. But then I will want, goodness. Okay, let me fix this. Right, fixed. And now we just take our carry line and we plop it down. And this is the setup. Except actually, ooh, I haven't considered this. So I did say that these carry and no carry meant no carry in, but for this one, we also don't need a carry out. So, would that help me? Yeah, that could let me remove the end. Oof. So I will also want variants of these without carry out. So +1 carry out, +1. Wow. Okay, but wow, this, yeah, the problem is this kind of doubles the number I want, the number of components I'm gonna be creating, which, I don't mind. I'll just make double. I'll be back. Okay, I didn't actually need to double it because the no carry out options only make sense for when we have a carry in. So carry in, carry out, carry in, no carry out, carry in, carry out, carry in, no carry out. But when we don't have a carry in, then the carry out doesn't matter, right? So I just call them optional carry out, optional carry out. So that's that. Yes, I am going insane over here. You have guessed correctly. So now we have these +x things. And what I need now is I need +0 carry in, no carry out. +0 carry in, no carry out. I just plop it down here. And that's our optimized circuit for ++. This is my new ++. How much does it cost? 28. So this has a gate cost of 28 and it... What? Delay score. Oh, it has no delay score because we have no I/O. Let's take an 8-bit output and an 8-bit input. Input 8 bits. The delay score I expect to be huge. Yeah, 16. So 2816. Let's compare this to what I came up with manually without all this analysis. So I should have it under base 8-bit ++. Yeah, 2816. And that was also 2816, I'm pretty sure, right? But where was I? At const. Well, let's go into here. Yeah, 2816. Let's rename this into ++. So, but now, well, no, I'll keep it at const for now because this is a playground. But now, let's imagine instead of adding +1, I want to add something like, let's say, let's do a constant. Let's do some constant over here. So let's say I'm adding 16. Let's say I'm adding 24. Yeah, let's just do 24. Right, let's say I'm adding 24. So now, in order to add 24, I look here. These ones are no carry in, no carry out, right? So 1, 2, 3, 1, 2, 3. No carry in, no carry out +0. So these are just nothing. And I just do it. no carry in, optional carry out, okay. So 1, 2, 3, right? No carry in, no carry out. But once we have added something, I now have a carry out. So I start with a carry out. I still need a no carry in, carry out. So +1, no carry in, carry out, this one. And now I need actual carry in. And I need +1, carry in, carry out. No, I need +1, carry in, carry out, like so. Over here. Oh, oops, sorry, this is wrong. Because I do +1, right, for these two. But then I again do +0. So what I need is +0, carry in, carry out. +0. No. +0, carry in, carry out. +0, carry in, carry out. And here I don't need the carry out, so I can use +0, carry in, no carry out. Like so. And we end up with a lower gate score. So just like I expected, adding larger constants, or at least constants with the larger least significant bit, is going to be cheaper. Hopefully you can see the idea behind these. This is insanity, I know, but I think this was a fun exercise. I might transition my well, it's not might, I cannot be stopped, I will transition my and minus operators, which I defined previously, to this scheme. Right, so I'm not gonna do it right now, but again, it's gonna be absolutely trivial. And also I might eventually implement my +4 counter using, again, this scheme, except I will have +4. So this will be my +1, and it will go from there. So I think this was a fun exercise. And finally, that's gonna be it from me for now. Next time, I won't be doing assembly challenges. I still intend to finish the functions section.